Alright, this video has the solutions for the AB with calculator test. Let's get cranking on them. So on the with calculator part, I think I've told you a couple times now, probably going to use your calculator on about half of them. Let's just count real quick. Let's see. So that looks like a calculator. This looks like you could probably do it without, but I guess we could count that as with. So 1, 2, 3. You can tell by looking at the answers, right? 4, 5, 6, 6 of them, 6 out of 15. So I think I was counting one probably that you really wouldn't need it for. So that's what we should expect, something like that. All right, here's a function. It's continuous on this interval. Graph of f prime here. This is the slope of the function f. The derivative as shown above. On which of the following intervals is f increasing? So this is f prime. So f is increasing whenever the derivative is positive. Right? So that's 0 to 2 and 4 to 5. If you look at this graph and you're like, oh, it's increasing here and here, I mean, that is what a third grader would say, right? Oh, where's it going up? From here to here and here to here. You cannot possibly think that that is the correct answer. That's just too, it's just too not calculus, I guess. So don't choose that one. The height of an object at times greater than 1 is given by this height. What's the velocity of the object at time 3? So this is the height. The velocity would be the derivative of that, and I want that at time 3. Okay? I could, well, this wouldn't be that hard to do without a calculator. I think if it's calculator active, this is what I want you to do. I don't want you to find the derivative of that by hand. I want you to do this. I want you to go, okay, I'm finding a derivative and I'm plugging 3 in. So I'm going to go math 8. There's my derivative. Need a dx there, and then here I'm going to put my function using x's instead of t's because that's what my calculator likes. And I'm finding that derivative at x equals 3. That's what I would like you to do. There's no reason to go doing that by hand. Just in case you did and you're wondering if you got it wrong, what happened, the derivative of this would be 2t minus 16t to the negative 1, so that turned into plus 16t to the negative 2. 15 would go away. You'd plug 3 into that, which would be 6 plus 16 over 9, which is the same thing. Actually, did you see this? You're like, whoa, it's not the same. Well, this is because the calculator is doing like a numerical approximation of the slope, but it's certainly going to be good for us to the decimal places that we need. All right. Number 78, function g is differentiable and satisfies that g of 1 is negative 4 and g prime of 1 of negative 1 is 2. What's the approximation using the tangent line? Well, this is the point and this is the slope here. So the tangent line would be y minus 4 is equal to the slope times x minus negative 1 or plus 1. What's the approximation for this? So that'd be y is equal to, I'm going to move the 4 to the other side, 4 plus 2 times, if you have negative 1.2 plus 1, that's just negative 0.2. So that's 4 minus 0.4, or 3.6. Number 79. Tara's heart rate during a workout is modeled by the differentiable function h, where h of t is measured in beats per minute, so that is a rate, and t is measured in minutes. Which of the following expressions gives Tara's average heart rate from this time to this time? So average value of a function is that, right? That's how you find the average value of a function. That's from section 7.6. That's where we learned that. So average value of a function. This is her heart rate function, so I want the average value of that function. So that would be this. All right. Let g be the function with first derivative of this. If g of 2 is equal to that, what's the value of g of 5? This is just fundamental theorem, right? If you know the g prime function, you want to get back to values of the g function, then I know fundamental theorem of calculus says this. That's section, I don't know, 6, let's see. It was early chapter 6. I think I just had it in there as fundamental theorem of calculus. So if you need any reviewing of that, that's where you can find it. So here I'm going to do this with the calculator. Clear that out of there. So that's math 9. I want the integral from 2 to 5 of the square root of x cubed plus x dx. And I'm trying to find g of 5. So g of 5, I'd have to add the 2, add negative 7. Right, this is negative 7, so that's the same as adding negative 7 is the same as subtracting 7 here. Oops, wrong name of function. So that's what I'm doing with my calculator, right? Moving that to the other side, and I'm finding g of 5. So that minus 7 is 13.899. Right? There's the one for the person who forgot to subtract the 7. I just did the integral of that. Be careful. Don't be that person. Number 81. If f is a function that has a removable discontinuity at x equals 3. A removable discontinuity is a hole, which means like it could be fixed. This, you can't fix that without like really seriously unrecognizably changing the function. So unremovable discontinuity means hole. And if you're like, well, that's a hole. No, this is a jump. This is a jump. This is a vertical asymptote. This, my friends, is a hole. That's a removable discontinuity. That's what that means. That's like a vocabulary question, really. All right. Let f be a continuous function such that this, what's the value of 0 to 13? So let's see, 0 to 13, I've got 0 to 17, 17 to 20, and then 13 to 20. So if I add these together, if I take 0 to 17 and add 17 to 20, that would give me the area from 0 to 20, right? This is back in, these rules are, I think this is like in section 3.2 or something. No, sorry, that's derivative stuff. Early, it's like 6.5, maybe, that we got these rules. Just basic area. I mean, if we think about this as area, 0 to 17 plus 17 to 20 has got to give you 0 to 20, right? Just sticking them together. And that would be this plus this, that would be 5, right? 8 minus 3. And then, if you want 0 to 13, well, you could take the 0 to 20 and then subtract the 13 to 20, right? and that would give you 0 to 13. Because if you've got the area from 0 to 20, that whole area, and then you subtract 13 to 20, subtract that off, then you get the 0 to 13, right? That hopefully is fairly obvious geometry to you. So 0 to 20 is, we just found that that's 5, minus the 13 to 20 is 7, so it would be -2, what we're looking for. Number 83, function defined above where k is a positive constant for what value of k, if any, is f continuous. So if f is going to be continuous, then that means when I plug x equals 3 in here and x equals 3 in here, I need to get the same thing, because this is like the open circle part of it, and this is like the dot part of it, and I need them to link up if it's going to be continuous. So I plug 3 in here, and I plug 3 in here, and I set these two things equal to each other. There isn't really any great way to do it just using algebra. Well, actually, you could, I guess. You could multiply this up. Oh, no, just kidding. I was thinking it was difference of 2 squares. So I think this is a little bit of calculator work to see, like, do you know how to solve an equation like that with your calculator? Two different ways to do it. You can get everything on one side. This is my preference. Equal to 0, because then I can graph that and look for the zeros of it. Or you could graph this and that and see where they intersect. That's another way to do it. But I prefer this, so let's get that in the calculator. So x cubed plus 3 minus 16 over, I should do that as a fraction, right? Over, you don't have to do it this way, but it looks nicer. It looks more like the actual thing you got there. Okay, so that's what I'm graphing. Where should I set my window from? Well, if it's going to be an answer, it's going to be somewhere between 2 and 9. So I'll just do 0 to 10 then. My window from 0 to 10. I don't really care what the y, min, and max are, so long as it crosses over 0, because I'm just looking for where it crosses. So 2 and change, so it looks like probably this, right? Because it's real close to 2. But you can go ahead and find it. Second, calculate what is the 0 of this. Left bound, I'm just going to go between like 0 and 4, let's say. 0 and 4. Yep. All right. Table above gives values of a continuous function. We don't know that it's differentiable. That's what that should, little red flag should go up there. They're not, it's not necessarily a smooth curve. It could have like sharp corners. Function f, it selected values of x based on the information in the table. Which of the following statements must be true? All right, so this goes from -5, -9 to 0, 1 to 2, 5. But it could have sharp corners. F has at most 1, 0. No, it could. We don't know what happens in between those, so it could cross. It definitely has to have at least 1. It doesn't have to have more than 1. Or it doesn't have to have only 1, rather. F has a relative maximum at x equals 2. Well, that doesn't have to be true. That would only be true if we were only looking on the closed interval here to here. Then that endpoint, actually, then not even that, because it could go up and come down again. So no, that's not true. There exists a value c where somewhere in between the x values -5 and 2, the f of c is 4. That does have to be true because this is continuous. If you imagine that horizontal line at 4, it does have to cross this, so that does have to be true. We don't know if it's differentiable, so this would be like a mean value theorem thing. If you do this, rise is 14 over run is 7. The average slope of this is 2 rather, 14 over 2. 14 over 7, which is 2, sorry. 14 over 7 is 2. So this would be true by the mean value theorem if the function f was differentiable. So this is really the intermediate value theorem, which we ran across in section, maybe it was early chapter 2, like 2, somewhere in chapter 2. You can find the intermediate value theorem. Actually, it might have been late chapter 2. So that's C. 85, function f is an antiderivative of the function g. So f is an antiderivative. F is antiderivative of g, which is the same as saying f prime equals g, if you take the derivative of both sides. That's probably going to be useful for us. Which of the following is the x-coordinate of the location of a local maximum for the graph y equals f of x? Well, this is f prime, right? Because f prime and g are the same thing. So if I want to find a local maximum, then I need to find where this f prime goes from positive to negative. So I'm going to graph this and see if I can find a place where it goes from positive to negative. And I'm going to have to change my window there. So I'm going to graph this, 3 minus the square root of x squared plus x plus 4 cosine x. I haven't checked, that's the first time I'm using a trig function here. I have not checked yet to see, to make sure that I am in radian mode. I am, good. So then I'm going to go to my window. I think, looks like if we're looking negative 4 to 4, looks like where all those answers are. And just need to see where it goes from positive to negative, so that should be fine for my y min and my y max. I'm going to graph it. Ooh. There we go. So right around 3. So that's actually, that would be going from negative to positive. That would be a minimum there. So it looks like it's right around 3.14 or so. That's the only thing that's close to where it crosses, so I'm confident in that, but you could do your, oops, to my graph, you could do second calculate and find that 0 where it crosses here. It's definitely between 2 and 4, right? So 2, 4, and there it is, 3.140. 85 is D. Number 86, graph of y equals f of x on the interval from 0 to 5 is shown above. It's an open interval. I don't know if that's important, but I'm just noting that those are not, they don't have equal signs. So could be like that. Which of the following could be the graph of y equals f prime of x? Okay, so here's a graph of f. What's the slope look like? Well, here the slope looks like it's some positive number, and it's a straight line, so it's some positive constant. So that's like this, right, from 0 to 2. So it ain't that. And then what happens after that? Then there's a jump in the slope, and it very abruptly changes to negative slopes, and then the slopes get closer and closer to 0. So at 3, it has 0 slope. So at 3, the slope is 0, and it goes from having negative slopes to that 0 and then into positive slopes. So it looks like that's going to be A. Yeah? What would this look like? That would look like that's kind of a weird thing to have like just a hole there in the slope, but that would look something like, this would be the upside down of that, going from positive slopes to the zero slope, more into negatives. So this is the correct answer. 86 is A. Looks like calculator active here. At times between 0 and 2, not including those, the velocity of a particle is given by that. Let time equals b be the time at which the particle changes direction from moving left to moving right. So that's when v goes from negative to positive. What's the total distance traveled by the particle during the time interval from 0 to b? Okay, so the first thing I have to do is figure out what that time b is, where it goes from negative to positive. So let's get this in. T sine t cubed. Oops. Right, and then I want to look at the graph from 0 to 2. If you don't do this window adjustment, I think you just run the risk of confusing yourself. Okay, so we want to see where it goes from negative to positive. And that looks like it's here. So I'm going to go do second, calculate, and find that 0. That is somewhere between, well, if you don't want to pick numbers that makes you nervous, I would say probably like between 1.7 and 2 would work, but you can play the game with the cursor and do left bound, right bound. You can do that. So b is equal to 1.845. So you want total distance traveled. The total distance traveled, remember how to do that. This is from section 6.7, I believe. What we can do with integrals with one-dimensional motion. Total distance traveled is the integral from wherever to wherever, so 0 to this, 1.845, of the absolute value of velocity. Those absolute value signs are key. If you don't put the absolute value signs in there, then you're finding displacement, not total distance. So with or without the absolute value signs, the difference between displacement and total distance. Total distance always positive, so that's why they're there. So let's see. I want to find, I already have this graph in here. You could go back to the home screen and just do it here. You could just do math 9. I want to go from 0 to 1.845, and in here I want the absolute value, which is math, which is number 1, of the, and I could type this in again, or since I have it in as y1, I could go to my variables menu, and I could go over to y variables, and in my function menu, it's in the menu as y1, so I can just put it in as y1 if I want to, and then do that. That's one way to get it. .011, so that's C. The other thing you could do is you have this graph here, you could go to y equals and say, you know what, I want that to be an absolute value sign, so I could do second insert and math, or I could put, there's a way to copy this. I don't know how to do that. I'm embarrassed to tell you. So I could just do this, math, number, get the absolute value signs there, and then put y1 in there, or you could retype it in if you want. It's just some options that you have. And then I'm going to turn this one off by hovering over the equal sign and pressing enter. So now if I hit graph, it's going to give me boing, boing. That's why the absolute value signs make everything positive. And then if I want to do math, second calculate and find number 7, it's just another way to do it, from 0 to 1.845, and this way it actually shades it in, which is kind of fun. So there it is, same answer. All right, there's some options for you. Let the function f be defined by this. For how many values of x in the open interval from 0 to, oh, maybe this is calculator too, is the instantaneous rate of change of f equal to the average rate of change of f? What? Okay, so I'm going to find, there's a couple ways you could do this also. One of them would be to just find these things. The instantaneous rate of change of f equal to the average rate of change of f. So let's find that average rate of change. The average rate of change is just slope. So those are my x values. And then I would have to do f of 1.565 minus f of 0. That's how I would find that average rate of change. So these are both 0, right? So if I plug in here 1, here's another trick. You can keep typing in that 1.565, but I don't really want to do that. I want to do 1.565. I'm going to store that as x. So now every time I type x, my calculator thinks it's that number because I just told it. If I hit clear, uh-oh, is it still there? Yes, I didn't clear that. I'm just clearing what's on the screen. So then I can just type this in as x to the 4th over 4 minus 2/3 times x cubed plus 1/2 times x squared minus 1/2 x. I can get that number, that's the top of that, and then divide by 1.565. Could have just put an x there also. So that gives me negative 0.392. This is my average slope, or average rate of change. The instantaneous rate of change is the slope of this. Well, slope of that's the derivative. That looks easy enough to just find by hand. 4 times 1/4 is 1 minus 2x squared plus x minus 1/2. All right, that would be the derivative of that. So I want to know on the interval from here to here, where are these things equal to each other? So I could just graph them both, right? That's one way of doing this problem. So here's my average slope. I'm just going to graph that. Negative 0.392. I'm going to graph that horizontal line, and then I'm going to graph my derivative and see how many times it crosses that line. So that's seeing how many times they're equal to each other. We're looking to find the number of times in this interval here. And I think that window should do okay. There's my horizontal line, and I'm going to cross it, looks like 1. Ooh, I'm going to have to zoom in around that line. Okay, so this is not a good window for y values. I'm going to zoom in from like -1 to 0 there. I need to see that a little bit better. -1 and 0. There's my horizontal line. I'm crossing it 1, 2, 3 times. 88 is C. You could move that to the other side of that equation and like see where it crosses the x-axis. Up to you. Let g be a twice differentiable function with the first derivative is positive and the second derivative is positive, so that means it's increasing and concave up. So it looks something like this. It's going up and bending up, such that g of 3 is 12. That'd be like 0.312, and then g of 5. I like these little sketches. They help me kind of picture what's going on. Which of 20, 21, and 22 are possible values for g of 6? Okay, so g of 6 is like out here somewhere, right? So it's bending up more. So I think the idea here is if the average rate of change here, here's 312, here's 4 comma I don't know what, here's 5 comma 18, and here's 6 comma I don't know what. So from 3 to 5, the average slope is 6 over 2. So it's going up an average of 3. But since it's concave up and it's bending upward, the amount that it actually has to go up has to keep getting bigger. So like for example, this couldn't be that, because then I would have an average slope here and then the same thing. Like it couldn't be increasing and concave up and do that. So like that would have to be like a possible value for this could be like maybe 14, because then it went up 2 and then it went up more than that. So all I know for sure is that it's going up an average of 3, 3. So when it goes from here to here, this has to go up more than 3. Because from 3 to 4 it had to go up at least 3, at least 3, and then this would have to be going up by more because of the concave up, because it's bending upwards. So that has to be something that's bigger than 21. So it could only be 22. It couldn't be 21 because then the average slope would be the same and it wouldn't be able to be concave up. Sketch really helps. Last one. Table above gives the value of the differentiable function f and its derivative at selected values of x. If g is the inverse of f, which of the following is an equation of the line tangent to the graph of g at the point where x equals 2? Okay, this is somewhere in chapter 4. I think this is section 4.3 maybe, where we talked about this inverse kind of relationship. Where x equals 2, so on the f function and the g function, where x equals 2 on the f function, that would be the point 2 comma something. On the g function, it would be the point something comma 2, right? Where that something is the same. So first of all, when x equals 2, f of x is equal to 1. So this would be 1, 2. And then if I find f prime of 2, then, and I switch that, make it upside down, that's going to be the same as the slope of the inverse at that point. Right? You can go back and review the notes. This is in 4.3. So what's f prime of 2? F prime of 2 is 4. So that means g prime of 1 is 1/4. So, but I want the graph of g at the point where x equals, dang it. Okay, so that's all true, but it doesn't help me because I want to make the graph of the tangent line where to the g function where x equals 2. So I need that to be 2 there. Okay, so if this is all true but not helpful. That would be helpful if we were making either the graph of the tangent line to the g function where x equals 1, or the graph tangent line to graph of f where x equals 2. So I need the 2 to be here. So that means something comma 2. Well, the thing you have to plug in, the x value to get 2 in the f function is 3. So that means that, and then f prime of 3 is equal to the slope There's 5, so that means g prime of 2 is that upside down. So the slope would be 1/5, and that's the only one that has the right slope. You can check the rest of the details. X minus 2, and there's the plus 3, so that's it.